Okay, if you open up the Week 11 Materials folder, inside the Excel folder, you should find an Excel workbook called W11D2. This is where we're going to have 3 examples of hypothesis tests that we're going to go over today together. Let's consider our first example. Your friend claims that the mean amount of time that college students spend watching Netflix each day is at least 130 minutes. Now remember, our first step in any hypothesis testing approach is to write out our hypotheses. So the first thing to notice here is that we're talking about a mean. This will be important once we start contrasting this against hypothesis test for other population parameters. But we're talking about a mean, so our null hypothesis and alternative hypothesis should be in terms of a statement about mu. And in this case, the claim that we're testing is that the mean, or mu, is at least 30 minutes. All right, so this includes 130 minutes in the claim. It could be 130, it could be 132, 145. So our claim here is that mu is going to be greater than or equal to 130. And as such, our alternative hypothesis is just going to be the other possibility. Well, if it's not greater than or equal to 130, then it has to be less than 130. And we know from our discussion before, when we have null and alternative hypotheses of this particular form, we know that we're dealing with a left-tailed test. And remember, we look towards the alternative hypothesis to figure out which way that inequality is sort of pointing, if you think of it as an arrow. So in this case, the type of test is going to be a left-tailed test. And what this means is that the region of extremity is going to be to the left of our test statistic that we compute from our data. This means when we go to find our p-value, we're going to look at the probability that a t-distribution is less than or equal to our test statistic. In other words, we're finding the probability in this left extreme tail. Our next step, we need to gather some sample statistics from our actual data set, and then we'll convert this using our formula. We'll convert this into a test statistic, or a t-hat value. Okay? So pause the video, do just as a practice of your Excel commands, figure out your sample mean, sample standard deviation, and sample size. Okay, so just some heuristic ideas here. First of all, notice that x bar 118 is much less than the claimed population mean of 130. So we're probably leaning towards believing that this null hypothesis is false. However, is it different enough? Is it far enough to the left in order to warrant rejecting that null hypothesis? That's why we need to convert this thing into a test statistic and compute a p-value. Does it reach that burden of proving beyond a reasonable doubt that our null hypothesis is false? So remember, when we compute our test statistic, I usually put the denominator, this s over square root of n, in a separate cell, just because it makes actually computing our t-hat value a little bit easier. We can put the difference of our two means in parentheses and then just divide by a cell reference. So I'm going to do this ahead of time. I'm going to take my sample standard deviation, divide by the square root of my sample size. So I'm just looking at the denominator here, this s over square root of n, and I'm computing that separately. In statistics, we often call this the standard error, but we're not going to worry too much about the nomenclature. For our test statistic, we want to look at the difference between our sample mean and the proposed population mean from the null hypothesis. So we're going to take the 118.6 minus 130. And again, we're looking at the hypotheses for this proposed population mean. And then we'll divide by this s over square root of n, which we put in a separate cell. So we can just cell reference that. So we have a test statistic of negative 2.48. Now keep in mind with our picture, since we're dealing with a left-tailed test, right, we're trying to find the probability of in the tail to the left of that test statistic. In other words, we're trying to find the probability t is less than or equal to our t-hat value. So this p-value, when we go to compute it, is going to be t less than or equal to the negative 2.48 if we're rounding. Notice this is already in cumulative form, so we can jump directly to using t.dist. This is how we get probabilities, right? A .dist command always gives us probabilities. And then the type of probability distribution we're using is the t-distribution. So this prompts us for three things. The first thing we want is the score. The second thing we need is our degrees of freedom. We can do this in our head, 74 minus 1 is 73, or we could even just type it out as our n minus 1 inside of our t.dist formula. And remember, the cumulative command is always set to true. And this is true for binom.dist, this is true for norm.dist, etc. So here's our p-value, 0.0077. Our significance level, which is sort of the threshold we need to meet in order to reject our null hypothesis, we need to be below our significance level, is provided in our problem next. So we have using a significance level of 1%. So the significance level of 1% is referring to our alpha value. So this is 0.01. And we can check. We reject our null hypothesis if our p-value is less than our alpha. And if you want to, you can actually do this as an inequality in Excel, and it'll tell you true or false. We can also just eyeball it. 0.007 is going to be less than 0.01. All right, so in this case, it's true. The likelihood of seeing a sample like ours is below the 1% threshold that we're setting, our significance level. So the short answer here is to reject our null hypothesis. But obviously we want to clean this up so it's a little bit more intelligible to people who aren't taking a statistics class. So we have sufficient evidence to suggest that our friend's claim is incorrect. In other words, the mean time spent watching Netflix is not 130 minutes or more. Another way we could phrase this, which is exactly equivalent, would be rather than saying we're rejecting H0, we could say that we provided sufficient evidence to support our alternative hypothesis. So we could also say we have sufficient evidence to suggest that the mean time spent watching Netflix is less than 130 minutes. Here's our second example where we're going to test a claim by a biology professor that the mean amount of time required to complete a cycle on the Krebs cycle is 30.8 minutes. We're going to use a simple random sample of quiz times provided in A2 to A151 to test the professor's claim. All right. Now remember, our first step here is to write out our hypotheses. We'll notice by reading through the problem that we're talking about a mean. So these hypotheses are going to be referring to mu. We also know that the claim by the professor is that the time required to complete this quiz will have a mean of 30.8 minutes. So we're dealing with exact equality. Mu is equal to 30.8. Which means our alternative hypothesis is that we're not equal to 30.8. And remember, when you're not equal to something, it could be because the true mean is bigger or the true mean is smaller. So what we end up with this set of hypotheses is something called a two-tailed test. We're going to actually look at the likelihood in two extreme regions, one to the right and one to the left. So the type of test we're working with here is a two-tailed test. Okay, now at this point we've done a few examples where we grab sample statistics and we use our formula to compute t-hat. So maybe it's a good idea to pause the video and try to do this entirely on your own in Excel, and then check your answers when we get to the end. We'll do the p-value together. All right, so we now have a test statistic of a negative 2.658. Now, if we think about, I'm going to move this over here, the absolute value of t hat in this case is just going to be 2.658. And so the reason that this is important is because when we go to think about labeling our picture, we're going to put the positive version, so 2.658 here, and then we'll have the negative version, which is actually our original t hat, negative 2.658 in this tail. And remember, when we go to compute the p-value, we want the area in both tails, but we use a little trick to do this. What we do is we just find the area in the left tail, and since it should be the same as the area in the right tail, we double it. So for our p-value, we're going to write this as 2 times probability, I'll say left tail, probability in the left tail. And we're just going to keep in mind that what this is, it's equal to 2 times probability that t is less than or equal to whatever the negative version of our test statistic is. In our case, our test statistic was already negative, so we'll just do a negative 2.658. So we're just going to double this t.dist command. Notice that this right here is already in cumulative form, so we don't have to do any further tricks when we're computing this. We jump right to a t.dist. So we take 2 times t.dist. Our test statistic's already negative, so we don't have to change the sign to the negative. Our degrees of freedom is going to be 149, remember n minus 1. And cumulative, we always set to true. So this is our p-value for this particular test. It's a 0.008. Now, we need to compare this against our significance level. And remember that whenever our p-value is smaller than our significance level, this means that we should reject the null hypothesis. Our significance level is 5% in this case. And so, yes, p-value is less than alpha. So, short answer, we're going to reject H0. But the way that we need to write our conclusion is something that will make sense to the general public. So, we have sufficient evidence to suggest that the mean amount of time required to complete the quiz is in fact not equal to 30.8. I want to make just a subtle note here. Notice that even though I have an x bar that's less than the proposed mu value, I'm not concluding that the mean amount of time is actually less than 30.8. Your conclusion should never extend beyond the actual null and alternative hypotheses that you set. That's what you're testing, that's what the results will be. So even if the data is suggesting that the quiz time is actually shorter, we still aren't going to conclude that way because we set up a two-tailed test, so that's how our conclusion needs to stay. So we would say we have sufficient evidence to suggest the mean amount of time required to complete the quiz is in fact not equal to 30.8.